Hello and welcome to today's 181 video. Today we'll be talking about generative classification. In our most recent video, we did something called discriminative classification, and if you remember, we used a logistic regression to figure out the probabilities that different data points would be in different classes. This is often referred to as discriminative modeling because you are teaching your model to discriminate between the classes to identify which class a data point is in, and that's the entire problem that you're solving. So today we're going to try and dig a little bit deeper into the problem and use a model called a generative classifier. And what that means is we're going to use Bayes' rule and some hypothesis about how the data is generated in order to make a prediction about the joint probability, the probability of getting some data point that has covariance X and is in a certain class. And then we're going to use that to eventually tell which classes we think we should sort the data points into. So you're sort of modeling the entire process as a whole, as opposed to just trying to get a model that can figure out which is the best class to put something in. So how are we going to do this? The generative process that we'll be assuming is here in red. We will be, we'll hypothesize first for any data point that we're generating. First, we pick a random class to put it in. And it will be in class I with probability pi. And let's say there are k classes. So pi is just a vector of class probabilities. And then after we pick what class this data point is going to be in, then we'll draw x from some multivariate normal distribution. And the multivariate normal distribution will have mean mu sub I. So based on its class, it'll have a different mean. And we'll say that all the regardless of what class it's in, that multivariate normal will have covariance matrix sigma for now, just as a little bit of a simplifying assumption. So notationally, we're going to assume that we have k classes. We're going to assume that every data point is like x, which is the actual data, and then y, and y is going to be a one-hot vector, so that means it's going to be a k by 1 vector, and if it's in class I, the ith element of that vector will be 1, and the rest of them will be 0. Again, thinking back to our logistic regression and softmax video, we recall that this is really notationally convenient when we're writing out the math and taking derivatives. So we're going to use MLE, maximum likelihood estimation, to find the best parameters. So suppose we're given some data set, X and Y. Then first what we want to do is write out the likelihood, right? We assume that our data is fixed, and we have, if we guess some pi and some mu and some sigma, we want the probability that we would get our data. And we want to pick the pi, mu, and sigma that give us the highest likelihood of getting our data. That's the idea behind MLE. So again, we assume that all the data points are independent, and so we just take the product of the likelihood over all the data points. And for every data point, if it's in class I, then the probability that we are going, the probability of getting X and let's say class I given pi, mu, and sigma is just the probability of getting class I, and I've just dropped the conditionals for notational convenience, times the probability of getting X given being in that class, right? And that's exactly what we've written here. First, pi I is the probability of being in that class, and then this, again, a little bit of an abusive notation, but this is the conditional probability of getting that X value given being in that class. And then this is where the one-hot vector comes in. We raise it to the power of y sub ni. And y sub ni is only going to be 1 for 1 for each data point. And so we'll only get the term like probability of x comma ci, where I is the true class that that point is in. So this gives us the likelihood of our data. And from here, we're going to take the log. Again, this is a very effective strategy when you have lots of big products. So the products will turn into sums, and then the exponent will come down, and then we'll just have log of this. And now we're going to use MLE. So we're going to find optimal pi, mu, and sigma. So let's go ahead and start by finding the optimal pi. So we'll go ahead and take the derivative with respect to pi j of the likelihood, And then we'll tack on an additional term, which is the constraint. So we're going to use a Lagrange multiplier here to enforce the constraint. The constraint is that the class probabilities must add up to 1, because every data point is going to be in one class. And so now we're going to just start getting rid of terms that are not dependent on pi j, because when you take the derivative with respect to pi j, those terms will just go to 0. So we can just get rid of them now. So the first thing to realize is over this first sum right here, if I is not equal to j, then this term right here will have no dependence on pi j, because this is the only point of pi dependence, and if I is not equal to j, then pi I is not dependent on pi j. So the only terms in this sum that we care about are the ones where I equals j. So we can just delete this sum and only count the terms where I is equal to j, which is what I've done here. In this second part, in the constraint, lambda, negative lambda times negative 1, we're not going to care about. And then all of these pi's we're not going to care about, except, again, the one where I is equal to j. So that's what I've done down here. Great. Now we're going to use log rules to split this log up into 2 parts. And you'll notice here, this has no dependence on pi j, so we'll just end up getting rid of that. Then we'll take the, and that gives us this thing down here. Then we'll take the actual derivative. Derivative of log is just 1 over x. And that can be pulled out of the sum since pi j has no dependence on n. So we just go ahead and we take the derivative, we pull it out, and we get this, again, which is equal to 0 right here, as we said at the beginning. So that implies that we can move the lambda to the other side. We'll go ahead and get this, and then we can multiply everything by pi j, and we divide everything by lambda. So that gives us an equation for pi j, but we still have a little bit of an issue because we have this lambda in here. So we're going to go ahead and solve the constraint. I'm going to just refer, this is equation 1. I'll use it in a little bit, but I'll try to zoom out so that you guys can still see this. So again, we take the derivative with respect to lambda, which is just going to simplify to the constraint, like it is with the Lagrange multiplier. And then we're going to take 1 and we're going to plug it in here for every pi I, right? Because we have a solution for pi I. And that gives us that 1 is equal to, and I pulled the 1 over lambda out the front here. So it's just 1 over lambda times the sum from I equals 1 to k of, and then we substitute this part in, the sum from n equals 1 to big N of yin. And remember, yn is a one-hot vector, right? So it's only 1 in one of its arguments, and the rest of its arguments are 0. And so if we sum over all the data points over all the classes of all the value we're essentially summing over every single y vector, all of its values. Every single y vector, if you sum everything up here, you're just going to get 1 because there's only one argument that's 1. So this sum right here is just equal to the number of data points, or n. So now we have a solution for lambda. We see that lambda is equal to n. So again, we're going to plug back into equation 1, and we're going to get that pi j equals 1 over n times the sum over all data points of ynj. So that's just the number of data points that are in the jth class, which we'll denote as nj. So we see there's actually a pretty intuitive interpretation to the MLE here, which is that the class probability, the maximum likelihood estimation for the class probability, is just the fraction of data points that are in that class. And we'll see this pretty often when we do MLE. So we'll sort of get a result that we feel like is kind of intuitive. So now we're going to solve for mu. I'd recommend that you just go ahead and pause the video here and see if you can walk through it. It's similar, but definitely a little bit more difficult than pi. And then we'll come back to it. Okay, great. So now we're going to walk through how to solve for mu together. So again, we're going to take the gradient with respect to some mu j. Here it's a gradient, right, because we're taking it with respect to a vector of the likelihood function. Notice we don't need any constraint here. So now, again, we're going to do the same thing. We're going to separate everything out, and we're going to get rid of terms that do not depend on mu j. So here I've just separated the log out with log rules. And now here I plug in the PDF for the multivariate normal distribution. And we realize log of pi I is not dependent on mu I at all, so we're just going to go ahead and get rid of that. Now, I've used log rules to split up the normal PDF here, and again, see that this first term has no dependence on mu j, so we can get rid of that. And then we just go ahead, we pull this 1/2 out, we pull this minus out, and then the last thing that we do is, similarly to pi, we're taking the sum from I equals 1 to k, right? But the only part of this that depends on mu j are these mu i's, and they only depend on mu j if I equals j. Otherwise, this whole term here doesn't depend on mu j at all. So the only terms in this sum that we care about are the ones where I equals j. So we can just replace all of these i's with j's and then just get rid of the sum, which is exactly what we've done here. Note that we also replace this I because it's still within the sum. Great. So now we're going to go ahead and take the actual gradient. So I've just used matrix rules from the matrix cookbook to move from here to here, but I'll have a linked explanation. And now we're just going to go ahead and solve for mu j. So we see that this is equal to 0, as we said at the beginning, because we're solving for the maximum. So we're just going to go ahead and break up this subtraction. So we'll move the mu j over to this side. And then here, recognize one, that inverse of sigma is not dependent on anything, so we pull it out of the sum. And so is mu j, so we pull that out of the sum. So then we just have sum over all data points of y and j, which, as we concluded earlier, is n sub j, or just the number of data points in class j. So we rewrite this here, and then here we pull the inverse sigma out to the beginning. And now we have, now we can just multiply both sides by sigma to get this, and then we also divide both sides by nj, and we get this. And this is our MLE for mu sub j. So let's give it a little bit of interpretation. So this is just the average, right, over all the data points that are in class j. We took their x values, and then we just averaged this, which again has an intuitive interpretation. The mean of the multivariate normal from which the x's are generated for points in class j is just the mean over our data points of the data points that are in class j. Great, so now we're going to tackle sigma. And again, I'd encourage you to see if you can do this one on your own, and then we'll go through it. So just go ahead and pause the video. All right, let's go through this together. So first we're going to take the gradient with respect to sigma, and we take the gradient of the likelihood. Note that the likelihood does include this pi term, and so this is the likelihood up here, and there is this pi term, but pi I has no dependence on sigma. So again, just like in the previous derivation, so we just get rid of it. So I've just skipped that step, and I've only broken up the normal here, but in case that was confusing, then we go ahead and I've broken up the PDF for the multivariate normal using log rules. Here we see that this term doesn't depend on sigma, so we can get rid of it. That leaves us with these two terms here. Then I use matrix rules to get to this next step here. So we evaluate the gradient, and the gradient of the log of the determinant of a matrix with respect to that matrix is just negative that matrix, or negative of the inverse transpose of that matrix. And then the derivative of this with respect to sigma is this. These both follow from lines in the matrix cookbook, but again, there'll be a link on the screen for more explanation. Great. So now we're pretty well set up to just go ahead and solve for sigma. So we're going to move this to the left-hand side of the inequality, right? Because this is equal to 0. So we just go ahead and add that to both sides. Then we get this right here. We're going to go ahead and get rid of these leading inverse sigma transposes. And that means that we end up having this. Note here that the sum over all data points over all classes of y and I, as we discussed earlier, is just the total number of data points, because y is one hot vector. So if you sum up over all classes, it's or if you sum up overall classes its elements, then you're just going to get 1, and then if you sum 1 overall data points, you're going to get n. So we go ahead and we divide both sides by n. That's how we get this here. And then we're going to go ahead and post multiply by the transpose of sigma to get rid of this, but it also gives us this sigma transpose here, and then we can apply a transpose to both sides. That'll give us just normal sigma on the left-hand side, and then note that this is a scalar and this is a scalar, so we're really just taking the transpose of this. But if you take the transpose of this, first you switch them, and then you take the transpose, but the transpose of the transpose is just the normal vector, and the transpose of the normal vector is the transpose, so we end up with the same thing. Interpret our value for sigma. So I'm just going to rearrange everything a little bit so that we can interpret it a little bit better. So first I'm going to just go ahead and swap the sums. Then I will move the 1 over n inside the first sum, and then I'm just going to multiply by n over 1 and then divide by n over, multiply by n sub I and divide by n sub I inside of the first sum. And hopefully this is a little bit more interpretable. So I claim that this means that the overall covariance matrix is basically the weighted covariance matrix over all of the classes. And this here, this inside, is actually just the covariance matrix for class I, because y sub ni is only going to be 1 for the data points that are in class I. And so we're going to take essentially the sum over the data points that are in class I of this quantity, and then we're going to divide by the number of data points that are in class I right here at the end. And that gives you the covariance of the data points in class I. And then we're going to weight that by ni over n, which is the fraction of total data points that are in that class. So the overall covariance matrix is just the average of the class covariance matrices weighted by what fraction of the overall data points are in that class.